Okay, let's begin our lesson. So right now we show you how many years ago we still use the cart, how we use the cart to transfer our silicon wafer, to transfer our lot, how our lot. But right now, how we don't use the cart to transfer our lot. How the lot, what is the lot? The lot is the one box of the silicon wafer. Or the lot, we call it one lot, two lot, three lot. Or sometimes you will say you are responsible for one lot, and the other one is more busy or more busy. He will say, I am responsible for two lots. Or later, or after watching this video, you can tell me how many wafers are there in one lot. How many wafers are we talking about in one lot? Or TSMC call it lot. Intel call it box. Okay, don't worry about it. How lot and box. How it means the same thing. How later you will see and right now how we watch the video, you will know what is the lot. What is the lot and how many wafers are there in one lot. Okay. And also you will see how can we transfer our wafers. Okay.
It's the most sophisticated manufacturing process in the world, and it's probably the most automated manufacturing process in the world. And so that in itself is challenging. We're always on the cutting edge. Our wafers are 12 inches in diameter, and we move 25 of them at a time in a box. And it just weighs too much for one person to do repetitive moves, so we had to automate it. When we talk about the vehicles, it's part of our AMHS system, our Automated Material Handling System. It's the transportation vehicle that picks up the product and delivers it to the process tool. It takes it from the process tool and delivers it to the next process tool. If the tool's not ready, it puts it in a storage unit. We keep track of the priority of what needs to move where first. We know where all the product is in the factory at any given time. In the old days, if our automation went down, it probably wasn't as important. The factory still ran. But today, if major parts of our automation system goes down, the factory stops. I think what excites me about what Intel does is the computing capabilities that we make possible that make people's lives better and more enriching.
Can you tell me how many wafers are there in one lot? How many? Yes, perfect. How very good. 25 silicon wafers. Okay. When we talk about one lot, how we mean 25 silicon wafers. Okay. So do you think what is the lot? Do you see it's a single wafer, right? It's only the single wafer. And when you see when you see it's very bright, how bright silicon wafer, it means we already deposit the metal on the top of it. Okay. In IC fab, when we see this so shiny, very, very shiny silicon wafer, we will not use our hand to touch it. Okay. Of course, we don't want to degrade the electrical performance, but the most important is we don't want the any metal atom to contaminate your hand. Okay, I don't want to wash my hand, so I don't want to touch it. Okay, so in industry, sometimes when we do the measurement, we will be very, very careful. We will wear the gloves. We will not touch any of the silicon wafer. Okay. Okay, so this is the single wafer, but here, you see, one lot, one lot, okay? And of course, we have the name, we have a name for this, we call it FOUP. Later, I will give you the whole name. Later, we call it a FOUP. And later, you will also know why the color of the FOUP is the yellow color, okay? Later, you will know it, okay? But right now, you see, this is one lot. So we have 25 silicon wafer inside this lot. And of course, Intel call it box, but TSMC call it one lot. Okay. And also we show you this system. Right now we don't transfer our silicon wafer by human because it's heavy, it wastes time, and I don't want to waste my money. If I break this silicon wafer into pieces, I don't want to pay it. So we need to use the tool, and this tool we have the name. Let me see. Here, automated material handling system, okay? The name for this tool is the automatic material handling system, AMHS, okay? AMHS, automated material handling system, okay? AMHS. We use this system to transfer our silicon wafer from one processing tool to another one and repeat it again and again, okay? AMHS, okay? Automatic material handling system, okay? Or you can write down by yourself, okay? Maybe next year I will write down for you, but right now this year you can write down by yourself, okay? Okay. So let's go back to see our slide. So right now we have a brief summary for the previous page to show you the trend for this semiconductor industry. Okay. So and first when we talk about the chip performance, so there are three trends. The first one, critical dimension must goes up and or go down. Yes, very good. I hear what you say. We need to go down due to the Moore's law, right? If the gate length is smaller, you will know on current will be increased, right? So of course, critical dimension must be smaller because we need to accommodate more transistor in tiny chip, right? So we want to have higher density of the transistor, okay? So the critical dimension must go down, okay? How about the component? The component here is the device, okay? The textbook write down component, but component is not good. It's the device, okay? Device. The device per chip will goes up, right? Just means the transistor number will double, right? Transistor number will double every 18 months, okay? So if the transistor number can be double per chip without increasing the chip size, then the function, we have more function per chip, right? So the device per chip must going up, okay? And how about the power consumption per transistor, okay? I don't say the total power consumption, but I say the power consumption per chip will, of course, 100% it will go down, okay? The power consumption per chip, 100% it will go down because, as we mentioned, the operation voltage is reduced, right? And the off current will also reduce, right? So the power consumption per transistor will be go down, okay? So all of this trend, we follow the PPA rule, right? For the next generation transistor, all of the IC fab company, they follows PPA for the higher performance, the lower power consumption, and the smaller area, right? So we say PPA, PPA performance, performance. The second P is the power consumption. A is the area, okay? So of course, all of these three the three trend follow the rule of the PPA, okay? And how about the second one? The second item, increasing the profit for the wafer fab. If the TSMC want to make more money, of course the wafer size must going up, right? But so far, 12-inch silicon wafer is the highest one. I don't think we will develop the large silicon wafer. But I mean the trend, we want to make more money. We need to use the higher silicon wafer in order to have more chips, right? More chips per silicon wafer, right? So the wafer size going up, the chip size or the chip number can be higher, okay? And also we want the reliability, 可靠度, the reliability of the chip going up, okay? Because it means the yield can be 良率 the yield can be improved, right? The reliability of the transistor is higher. It can guarantee the chip yield is higher, okay? So the IC fab can make more money if the yield is higher, or they have more good chip to sell to their customer. So if the yield is higher, it means the chip, or they will have more chip to sell to their customer. Of course, they can make more money, okay? 良率高一点的话IC fab 他们才会有更多良率好的晶片可以卖给他们的客户，所以良率越高代表这些 IC fab 他们才能够越赚钱因为只有良率高，代表说它晶片好的晶片数目才多，那你卖给客户一定只能卖这些好的 performance 的晶片嘛所以你的良率越高，对业界来说通常都是一个赚钱的指标。Okay, and the next one, we will briefly show you the IC fabrication. But this IC fabrication is not in detail. It just shows you how can we prepare the silicon wafer and what is the package, okay? And the real IC fab process. We will talk about it several weeks later, okay? So right now, this slide only shows you how to prepare the silicon wafer, okay? This slide shows you how to prepare the silicon wafer only, okay? So the first one, silicon crystal growth. And the purpose, of course, detail, we have another chapter to show you the detail, but right now you just need to know the main purpose for the polycrystalline is we transfer the polysilicon to the single crystal silicon, okay? And right now the polysilicon is a very pure polysilicon, and we want to transfer to the single crystal silicon. Of course, it's also very pure silicon, okay? So the first purpose, we want to transfer the polycrystalline silicon into the single crystalline silicon. 这个步骤我们只是把它从多晶变成单晶的步骤但是它其实原先这个多晶它就是一个很纯的 silicon wafer， 我这边只是把它从多晶变成单晶。So the purpose of the crystal growth is we just transfer polycrystalline silicon into single crystalline silicon. And do you know why? Why do we want to use the single crystal silicon? Because the mobility will be higher. Why we use the single crystal silicon? Because electron mobility and the hole mobility can be improved, okay? When the electron mobility is improved, the NMOS on current can be improved, okay? And if the hole mobility is increased, PMOS on current can be increased, okay? So of course, we need to use the single crystal silicon. We need to make sure the mobility just means the ability for the electron to move, okay? If the electron can move smoothly, fastly, it means the NMOS on current will be higher because the carrier to conduct the current for the NMOS is the electron, okay? Likewise, we can also improve the hole mobility. And today, if you increase the hole mobility, then the PMOS will also have the higher on current, okay? So that's the reason 100% for the channel material, for the silicon wafer, we will use single crystal silicon, okay? With 100 plane, okay? So for this single crystal silicon, we need to make sure our plane is 100 plane, okay? And then after the crystal growth, then this polycrystalline silicon will become single crystal silicon ingot, okay? We call it ingot, in Mandarin is 金柱，金柱好像像一个柱子一样。So we call it ingot, we call it ingot. And right now it's the single crystal silicon ingot. It's very heavy. It's very heavy, around 300 kilograms. Very, very heavy, very large and very heavy. Okay. Later we have the picture to show you the ingot. Okay. And then the next step, right now we know we want the 12-inch silicon wafer, right? We know right now I want 12-inch silicon wafer, so I need to do the crystal trimming and the diameter grind. It means, right now I need to make sure my diameter, the diameter of the ingot is 12 inches, okay? So I need to make sure the diameter is exactly 12 inches, okay? And this is the one word here we use so often. I need to let you know, and you must remember it's the trimming. This word we use it a lot. Okay, what does that mean? Trim just means smaller. In industry, maybe it means the hair. Trim your hair, right? 剪头发那个 trim your 修整头发。Okay, the trim here just means become smaller. So we use trim in IC fab so often. We don't say the Chinese, we say trim. Or we will say the gate must be trimmed. Or it means the gate length must be smaller. Okay, but we will not say the gate length is too long. We need to be smaller. We will not say it. We will say we will trimming the gate. Or the gate must be trimming. Okay, we will say trim. This word. Okay, so. Usually today, for this is the cross-section of the silicon wafer. After we deposit, after we deposit the outside, and then we will define the gate area. We define the gate area. And then we will define the gate area. Okay. But sometimes the gate length is too long. We will say we can trim again. We can trim the gate. We will trim the gate. It means the gate length is too long. We need to use some process, some etching process, to remove the gate, to remove the edge of the gate. So we will use trim. Okay. So in the future, when you see the recipe in the IC fab, we have many recipes for the IC fab. We will use this word trim. Trim just means become smaller. Okay, trim, make everything become smaller. Not only for gate, you can for everything. Okay, for it, you can trim the metal line, trim the gate, trim the fin. Trim the fin. Trim 这个字我们用在所有的这个薄膜沉积上面，我们要让它变得更小，我们就会说 trim。我们不会说，这个 gate 要做小一点，我们会说这个 gate 拿去 trim 一下，这个 gate 需要 trim，我们要 trim gate，就是我们都把它有点中英交杂在一起。So next time when you hear trim, it means become smaller. We need it to become smaller a little bit. Okay. Okay. So right now, this trim here means we need to make sure our diameter is 12 inches, okay? And today, for the smaller silicon wafer, we have flat grinding, we have the flat grinding, but only used for the smaller wafer, only used for the 4 inches or 6 inches. Smaller silicon wafer, we will use flat, okay? For the 12 inches silicon wafer, we have notch, right? We have notch, so we don't use the flat. Flat only used for the 6 inches or 4 inches, okay? And then after that, we can we do the wafer slicing. So we have one wafer, two wafer in pieces. Okay. Then after that, we will do the edge rounding. So that's the reason when you hold the silicon wafer, you can see the edge is already rounding. You will not hurt. Okay, and also it will not damage so easily. It will not have some breakage so easily because the edge is rounding. Okay. 这个边缘 silicon wafer 的边缘都是有研磨过的。你可以拿去再摸一下，它其实边缘都是有研磨过的。因为它要避免一些应力集中，它其实主要是避免应力集中，倒不是担心你可能被刮伤，它是担心那个应力集中会让 silicon wafer 比较容易破裂。所以它的周围都是有研磨过的。OK。 The next one, lapping, wafer etching, and polishing. I can say lapping and polishing is very similar. For me, it's all very similar. Very similar. Just to remove some defect and also control the thickness of the silicon wafer. So for the process 7 to 9, I can show you the purpose is to remove the defect or remove the surface defect. Okay, you have some particle or you have some contamination, 污染物 particle, or we can remove all of this defect, particle or contamination on the silicon wafer by lapping 研磨出磨 by wafer etching 蚀刻 by polishing 比较像是细磨。 Okay, and the wafer etching in 蚀刻 okay. So by these three process, later we will still have a detailed slide to show you here. But according to this page, you have the concept. Okay, for this three process flow, we need to remove the silicon wafer defect on the surface. Also, we need to have the very smooth surface. We need to make sure silicon wafer has a very, very smooth surface. And also we need to control the wafer thickness. THK is thickness, okay? Okay, we need to control the thickness of the silicon wafer, okay? Later you will think about, yes, I want my silicon wafer clean, right? You want a clean silicon wafer. And right now you see the silicon wafer, you need to know this one is very clean, right? Very clean and very smooth surface, right? And also the thickness is well controlled. It's 775 micrometer. So you will know all of this purpose. You can achieve all of this purpose by using the processing 7, 8, 9. Okay, you want a clean silicon wafer, so it can remove the defect. Okay, you want a very smooth surface. Later I will show you why. You want a very smooth surface, so it can help you to have a very flat surface. Okay. Also, you need to control the thickness because we need to use the robotic arm to transfer the silicon wafer. So the silicon wafer surface must be the same. So the purpose we can control the thickness. Okay. 想一想，同学，你对半导体制程，你只要想一想你的 silicon wafer 看到是什么，你觉得它的要求是什么？基本上它的目的就是你看到这个 silicon wafer。你希望它又干净又平坦，然后厚度控制又要正确，那这就是你做这些制程的目的。所以你其实看一看 silicon wafer， 然后去感受它。其实有些东西你不太需要背，只要理解它就可以了。Okay. And finally, we need to check. We need to check everything is under control. Okay. Okay, later we will see the real one or the more in detail. Okay, and this is the ingot. So we slice into the silicon wafer. Okay. for the textbook, the textbook shows you semiconductor processing is a very long and complicated process, very, very long. And do you know how many processing steps do we have in order to finish the wafer? How many processing steps? You can get 有多少个制程步骤我们才能够完成一整片晶圆 ？How many processing steps? 1, 2, 100? Oh, actually, of course, the test will show you how this is the module 模组一些制程的模组。The test will show you we have the layering layering, doping process, patterning process, etching process. However, I can show you we don't say layering. We say the deposition. Deposition is the official name. Okay. We say deposition, 沉积, we don't say layering. Layering, we don't say that. It's weird, so weird. Okay? And patterning. It's not a formal name to say it. For the formal name, we will say photolithography. Okay? Photolithography. Photolithography in Mandarin is 黄光微影制程. Okay, so some people will say it's a 光刻, but it's not right. It's not the way we say it. Okay, if I see your homework to write down about 光刻, I know you copy from the ChatGPT. Okay, so don't do that. Don't write down 光刻 for your thesis or for your homework. Okay, or you can write down 黄光微影微影制程. Okay. So for the photolithography just means the patterning. Okay, we want to pattern a picture, pattern the gate. Okay, so for example, as we mentioned the gate, we can pattern the gate, It means we want to remove the gate here. We want to remove gate here. Okay, we only want to remain the gate in the middle of this pattern. Okay, so we can say pattern. Okay, but it's not an official name. Or for the formal name, we will call it photolithography. Okay, we call it photolithography. Okay, in industry we say photolithography. The department we say photolithography. The module we say it's the photolithography. Okay, and also the etching. Etching is 蚀刻 etching 蚀刻. We want to remove something, right? We want to remove something. So we have the department in IC Fab who is responsible for etching, removing some area. We call it etching. Okay. And doping, you already know the doping, right? How we put some atom into silicon wafer in order to change the electrical conductivity. Like N-type silicon for so strength, right? So doping, 掺杂, you already know the doping, okay? So we have different department in IC Fab, or the deposition department, the photolithography department, etching, doping. We have all of this module. You can call it module, okay? And I didn't tell you how many semiconductor processing steps. Usually it's over 1,000 processing steps. Or if you want to finish the whole silicon wafer, it's over 1,000 processing steps. Okay, but don't worry about it. Okay, because all of these processing steps will repeat and repeat again. Okay, so you don't need you are not necessary to learn 1,000. Or maybe you only learn 20 processing steps. It's good enough because all of these 20 processing steps will repeat it again and again. Okay, and do you know how long the semiconductor industry will take to finish the 1,000 processing steps? How long? 1 day, 2 days, they can work 20 hours a day, you know, in industry, of course, 20 hours a day, they work 20 hours a day. So do you think how long does it take for the IC fab to finish this IC fab and this fabrication? How long? What? 6 days? But 1,000 steps. 1,000 steps is a very long and very complicated process, right? So maybe longer is better. Of course, they don't want longer, but they do their best. IC fab already do their best. It still need 1 to 2 months to finish all of this semiconductor processing. Okay, and all of this processing is done by the tool, not by the humankind. Okay, so today one day if you are an engineer in TSMC, you will not see any of this semiconductor tool because you only working in the office. Okay, you're not working in the IC fab. Okay, so maybe you will not. You have no chance to see all of this processing tool in the future. Okay, and it takes you 1 to 2 months, or it takes you 1 to 2 months to finish all of this processing. Okay, and for all of this processing, how you need to make sure, how you need to control it, how you need to make sure, and this chip is fabricated safely and carefully. Okay, because you want to have the high yield, how you want to have the high yield. Okay. Also, I want to share with you. This is the office. This is the office in Intel. How do you think about this? I mean, the environment. One day, or think about it, one day, or several years later, if you can work in this environment, do you think it's good or bad? Good or bad? Not good? Can you tell me why? Oh, not bad? Not good, not bad. Don't worry about it. You can share with us your thoughts. Good? Not so good. Why? Compact? Stress? Oh, yes, it's stressful, but how can you see stressful from this figure? Oh, you mean they have so many screens, so many computers, right? For me, I think this environment, the office environment is so fantastic. Why? Compared to another company, you know what I mean, right? I mean, another company, you know, another one. I mean, I experience it. You know, you can see, or if you see here and your colleagues see here, you have your own privacy, right? Nobody will see besides you. Nobody will know what are you typing, what are you talking to, right? What are you saying anything. If you want to make a phone call, you need, or everyone knows what happened, okay? But you see how for the Intel, you see how the environment is so good. You still have some privacy, okay? But I mean, for the other company, just like, or maybe you need to pull these two tables together. This is the environment for the other company. You see, everything you do, your colleague know everything. They will know, your children is sick, your wife, what happened to your family, everything they know, right? You don't have any privacy, you know? So when I see, wow, the Intel office look like this, fantastic, okay? Also, you need to know, one day if you have an environment like this, so nice, so nice, okay? Okay, so, let's go back to see. Okay, so in IC fab, they need to make sure within these 1 to 2 months, they need to make sure 100 processing step is done carefully and safely because it's related to the year of the chip. So they need to make sure every semiconductor processing can be done safely and carefully. Okay. Later we will show you we will show you the defect related to the year. And right now this page just shows you the impact of chip size. Right now we talk about the chip size, okay? Why do we need to scale down? Why do we want to scale down? Of course, we want to have more chip. More chip means we can make money, right? If we have more chip, or if the chip size is smaller, or we have more chip, the chip number can be increased, right? So IC fab can make money, okay? And this is the first one. And the other reason is related to the year, okay? There are two reasons, or at least two reasons, why do we want to scale down our chip size? If you can scale down the transistor, of course, the chip size can be smaller. 假设我们今天根据摩尔定律，你的电晶体可以被 scale down， 可以被微缩。那我们假设在一样多的这个电晶体的数量之下，那你的 chip size 是不是可以也一起被萎缩、被缩小？There are two reasons why we scale down the chip size. The first one, we want to have more chip. Then IC fab company can make more money. Okay? And the second one, today if the chip size is smaller, the yield will be higher. Okay? The yield will be higher. Why is the yield? The yield means the good chip divided by total chip. And this year is a very rough year. Actually, in IC fab, they have a different definition for the year. But I don't want to go through in detail because later when you join the IC fab, you will know they have a different definition for the year. But this year just the general term, general definition for the year. Okay. So for the year, we say, and for the IC fab, they also have the year for the SRAM, for the memory. But right now we talk about the year for the chip. 良率的定义有很多我们一般讲的这个良率，我们讲的是一个比较从 chip 的良率来说明。但未来你在公司你会发现，它其实良率的定义，它不是对于 chip， 它可能小到一个记忆体，小到 SRAM 都可以定义为你 SRAM， 它可能256 megabit 的 SRAM 它的 yield 有多少。所以未来你在你不同的部门，你会知道良率的定义不是只有 chip， 你对记忆体它也是可以定义可能 SRAM 不同 size 的 SRAM 它就有不同的良率。OK， right now we see the year means good chip divided by the total chip. So today when you see the figure here, right now we have 4 defects. 1, 2, 3, 4. The same defect 1, 2, 3, 4. 4 defects. 4 defects. Okay. And before that, let me show you why do we call it killer defect. Yes, killer defect is also the terminology we use in IC fab. When we say killer defect, it means this defect will cause the chip function fail. Okay, so this defect is very, very important because it will cause this chip function fail. So we say this defect is killer defect, 杀手等级的 defect 它不是一般的 defect， 它是一个很厉害的 defect， 只要有它存在，你的良率就会掉。为什么？只要有它在，你的晶片就会失效。So we call it killer defect. It means once we have this kind of defect, and the transistor or the chip will function fail. So it's a very serious defect. Okay? Killer defect is doesn't relate to the defect size or defect type. Usually it's the location. Location is most important. The defect location is most important. 同学未来可以看killer defect 通常是什么？是很大一颗 defect 吗？不一定那个 killer defect 如果是很大一颗 defect， 它跑到一个鸟不生蛋的地方都没有电晶体，你的这个 chip 也不会死掉。通常 killer defect 指的是你的 defect 它落在很关键的地方，像是哪里？像是电晶体，像是金属线，那你的 defect 全部都叫 killer defect， 不管它大或是小。OK， I mean the killer defect means the location is very important. It's nothing to do like the defect type or defect size. So sometimes the defect is very large, but this defect doesn't near the metal line, doesn't near the transistor. So your transistor still function good. Then this defect, this big defect, is not the killer defect, okay? But today, once you have the small defect, but this small defect just happen to be located inside the transistor, then this defect is 100% the killer defect, okay? So the most important is not the type, the size of the defect. The most important is the location of the defect. It matters, okay? We don't have the example to show you. One day, if I have the example, I can show you that. For all of this killer defect, you see, the right finger and the left finger, we have 1, 2, 3, 4. 1, 2, 3, 4. 4 killer defect, okay? But today, for the wafer on the right, you can see Y means the ear. The ear means 2/6. 2 means that we have good chip. We have good chip. Where is good chip? Here, 1 and 2. Overall, we have 2 good chip. However, the total chip only 6. Only 6. So finally, the ear on the right only 30%. Okay, only 30%. Very, very low ear, right? Very, very low ear. So it can make sure the IC fab cannot make money. Okay, because only 2 chip can survive. Okay, only 2 chip can sell to the customer. Okay. However, today, if the chip size is smaller, like the figure on the left, okay, you see, today, if the chip is smaller, you see the chip, when the chip size is smaller, you see, overall, we have 28, we have 28 good die, we have 28 good chip, 28 good chip here, right? And we only have 4 failed chip, okay? And overall, we have 32 chip, okay? Because the chip size is smaller. So the figure on the left, right now we have 87, the ear is 87%, okay? We have more chance to have the good die, okay? So when you see this picture, you will know the chip size will be smaller, the better, okay? Smaller chip size can make sure you have the higher ear, OK？ 这张图我们是假设它的 defect 在相同的位置上面，然后每个 killer defect 都会造成这颗 chip function fail，所以你可以看到 chip size 越小，它的良率越高 ，OK？ But this is the one methodology to increase the ear. If I want to increase the ear, the first methodology, I can reduce the chip size due to the Moore's law, okay? But the most important is if I want to reduce, if I want to increase the ear, I need to reduce the defect density, right? It's more important, right? It's more important if I want to have the higher ear, I need to reduce this defect density, okay? I need to reduce the defect density. I think this is more important. So later, we will show you how can we remove all of this defect density by the RCA clean. Later, we will show you the process. We will show you the process, the parameter for the RCA clean. But RCA clean is a very simple, very basic clean method. But we use the RCA clean this process, we can remove the defect. We remove the defect by using this chemical solution to remove the defect. RCA clean. Later we have the slide to show you all of the detail for the RCA clean. But here, I need to tell you, the most important way to increase the ear must be reduce the defect density. Okay. Okay, we mentioned after we finish the semiconductor processing, then we need to do the electrical test probe because you need to make sure the chip is function good or function fail, right? So we use the electrical test probe. Okay, this probe can be none. If the probe can be none, it means the kind of the needle to contact with our wafer， 它可以当做是一个探针，接触到你晶片的探针。So the probe can be a noun, it means the needle to contact with the chip, or it can be a verb, We use the chip probing to make sure to do the test, to do the electrical test. So this probe can also be a verb, or it means we do the electrical testing, okay? And today, if we want to sell the chip to the NVIDIA, so you need to think about it. Can we test the transistor on each chip? Can I do that? I mean, for the NVIDIA, I want to sell the chip for NVIDIA or for the Apple. Can I test the transistor here or transistor here? Can I do that? Can I do that? I mean, today I need to make sure this chip is function good because I want to sell this chip to the NVIDIA. Can I do the electrical testing probe? On here, I mean the precision, the location here. Can I do here? Actually, it doesn't make sense, right? Because NVIDIA will say you already do the testing, okay? So the electrical performance will be worse because you already do the testing for so many times, right? How can you make sure the long-term reliability if you do the testing on my chip, okay? So usually, all the time, we cannot do the electrical testing on the chip because this chip we want to sell to our customers. So how can we do that? How can we do that? We need to test our transistor on where? On the swap line. Here is the swap line. The swap line is between the chip or between two chips. We say it's the swap line. Swap line is where is the location where we will use the laser to cut it as a die. Okay. So later we will use the laser. We use the laser. We will use the laser to cut and follow the swap line. We use the laser to cut off this silicon wafer into a small chip. Okay, so the swap line just means the waste area, the area we didn't need. Because later we use the laser, we will use laser to cut it into a chip. So this is the area we don't need. Okay, so we call it swap line. We call it swap line. So anything we need to test, we need to make sure our transistor is function good. Our transistor has high on current. We need to test it. We need to test it on the swap line. Okay, so it's very funny because every department, we will compete. If your department have better performance, then you will have a large area of the swap line. So maybe the yellow one for the team one, because your performance is better, and the red area for the team two, smaller area because your performance is not so well. Okay, so the different area we can get for the team one, team two, team three, for example. Okay, and for the different group, we can design different transistor we want for our area, and for this area we do the testing. Okay, so after we fabricate all of this chip, we say this testing as chip probing, CP, chip probing. It means right now we already finished. So we do the electrical testing, and this moment, this probing is the chip probing, CP. Okay. Okay. Next week, we will have a new handout. Okay, I will try to give you as soon as possible. Okay. Have a nice day. That's all for today's lesson.